Hello guys, today we are going to revise our chapter number 4, which is applications of differentiation. So we will divide it into two parts. The first part would be discussing the topics that we have studied in our chapter number 4, and then we will talk about the examples we can do, and you have to do those examples actually that will be given at the end of this PPT, right? Alright, so without any further ado, let's move to our first topic, which is maximum and minimum values. So when we talk about the maximum and minimum values, actually we have two kind of maximum and minimum values. First one is a global maximum or minimum, and the second one is a local maximum or minimum. So global maximum or minimum values are actually belong to the category where we discuss the highest or lowest values of the functions, right? And it is also known as absolute value. So what happens in this particular category, or in this particular type of the maximum and minimum value, we will take the highest value, right? Highest value of our function and the lowest value of our function. So when we see the definition over here, it says let C be a number in the domain D of function f, right? Then f of c is the absolute minimum value of function when f of c is greater than or equal to f of x for all x values in our domain. Understand? Similarly, it's when we have our f of c, right, and it would be absolute minimum value if f of c is less than or equal to f of x for all x values in our domain, right? So it clearly says that there are lots of values in particular domain, right? And we have the lowest value or any other value which is f of x, and our f of c is greater than or equal to that f of x. It means we have the maximum, absolute maximum value. And if our f of c is less than or equal to that f of x, it means that we have this absolute minimum value. Okay, now we move to the local maximum or minimum. So the concept is slightly changed over here. It's slightly different actually. When we talk about the local maximum or minimum, it includes a particular interval or a small region in a graph, right? So in the definition it says the number f of c is local maximum value if our f of c is greater than or equal to f of x when x is near c. So it means that there are lots of other values as well, but when it is closer to c, right, then we can just compare those values and we can find whether it's maximum or minimum. So actually it's talking about a small interval in that whole big function. Similarly, the number f of c is local minimum value if f of c is less than or equal to f of x when x is near c, right? I hope it makes sense because it's really easy and we have already talked about it. Okay, now there's another concept which is followed by these maximum and minimum values, and that is the extreme value theorem. Now in this particular theorem we say that if function is continuous on the closed interval ab, right? Remember, there are two things in this particular value theorem, which is extreme value theorem. Two things are involved. First one is it has to be continuous on the closed interval. Sometimes the functions are continuous but they are not closed interval and they are like going to infinity, right? They might go to the negative infinity or positive infinity, but we have to keep in mind it should be continuous and has the closed interval, right? And then it has to have these maximum and minimum values, absolute maximum and absolute minimum values in itself, right? So it says that if f is a continuous on the closed interval a b, then f attains an absolute maximum value f of c and absolute minimum value f of d at some numbers c and d in R a b. Understand? So that is actually the extreme value theorem, which involves two things. First one is it has to be continuous on closed interval, right? Second thing is it has to be these values, absolute minimum and absolute maximum values. Next is a critical point or a critical number. So critical point on a function is a point in which the derivative is either zero or undefined, which means that critical points occur wherever the slope of graph is completely flat, right? That whenever the slope is flat, we will say there's the critical point of our graph, which does not happen in, in every function. It doesn't happen. So there are some sort of functions which are free of these critical points, right, or critical numbers. So all extreme values can be the critical points, but not all critical points are the extreme points or extreme values, right? Okay, now when we go by definition, we see that a critical number of the definition f is number c in the domain of function such that f prime of c is equal to 0 or f prime of c does not exist. So it says that our critical number is actually a number c in the domain of our function whose derivative of f of c is equal to 0 or it does not exist. It is undefined, right? So that is the definition of our critical number. Okay, now comes Fermat theorem. In Fermat theorem, it says that if f has a local maximum or minimum at c, so a function has a local maximum or minimum at point c, and if the derivative of that f of c exists, right, then that derivative should be equal to 0. So that's the concept of Fermat's theorem actually. It says if f of x has a local maximum or local minimum at x, right, which is, let's say x is equal to c, so we will say that f of c actually, right, and then f prime of c, or we can say the derivative of f of c exists, and that derivative of f of c is equal to 0, which means that there is 0 slope. So in terms of critical numbers, Fermat's theorem can be rephrased as follows. If f has a local maximum or minimum at c, then c is a critical number of function. Yeah, which is a very simple kind of definition for critical number. It says if f has a local maximum or minimum at c, then c is our critical number of function or f. Okay, now we have this Rolle's theorem, and in Rolle's theorem it is actually built on 3 assumptions. So if we do not meet one of these 3 assumptions, then we can't use Rolle's theorem to prove the existence of a horizontal tangent line. So basically it's proving that there are tangent lines, right? Whenever there is a line passing through the graph, a tangent line, there would be another horizontal line which would be parallel to this tangent line, right? So when we see the Rolle's theorem, it says let f be a function that satisfies the following 3 hypotheses, right? 3 assumptions or 3 hypotheses that are: f is a continuous on the closed interval. This function should be continuous on the closed interval, that is ab, right? And then it should be differentiable. Just continuous is not enough, but if it is continuous, it would be definitely differentiable on the open interval ab, right? And then f of a should be equal to f of b, which is a third assumption or third hypothesis of this particular theorem. Then this theorem would be proved, right? And it says then there is a number c in AB such that f prime of c is equal to 0. So it clearly says that there should be 3 things in this particular theorem, and if these three assumptions are satisfied, then it would be proving our Rolle's theorem. So if there is any point of discontinuity, and the function is not going to be differentiable at the point, we have to know that if this is not continuous, this function is not continuous, then it would not be able to, we will not be able to differentiate this particular function, right? So you can see this particular example over here in on the left side. There is a figure of theorems, Rolle's theorem. Actually, I'm sorry, slip of tongue, it's Ramadan. So figure of Rolle's theorem you can see over here, and these are actually, you can see the f prime of c, which is derivative of f of c, is equal to 0. The slope is definitely 0, right, on the both c1 and c2 points. Okay guys, now we have another theorem, which is mean value theorem, right? And you can see in the graph or a figure over here for mean value theorem. So this mean value theorem tells us if function is continuous and differentiable on interval, then there must be a point inside of that interval where tangent line of our function at the point is parallel to secant line. Now we have to understand this concept of tangent line and secant line actually, because we know that whenever the line just touches a particular point, right, and goes away, that is called a tangent line. It is not intersecting actually, it is not cutting, but when a line cuts a particular graph or a particular curve, that is called a secant line, right? So in the mean value theorem, it says let f be a function that satisfies the following hypothesis. Our function is continuous on the closed interval, same, and it should be differentiable, right? The second situation also kind of similar or same. Then there is number c between a and b, which could be f prime of c, or derivative of f of c is equal to f of b minus f of a divided by b minus a. So that's how we calculate our derivative of f of c, right? Or equivalently, we will just find, we will sort out this mean value theorem with f of b minus f of a is equal to f prime of c, or derivative of f of c into b minus a. So that is actually about the mean value theorem. So in this mean value theorem, we have to keep in mind that it should be continuous, it should be differentiable, and then it should be, I mean, f of a should be equal to f of b. Sorry guys, that's not, f of a should not be equal to f of b. Actually, f prime of c, or derivative of f of c, should be equal to f of b minus f of a divided by b minus a. So this value actually, yeah, so this, it's about this value, right? The one I just spoke about was Rolle's theorem. It is not about this theorem. So in mean value theorem, we have to satisfy these two things, and then we have to know that our f prime of c, or derivative of f of c, should be equal to f of b minus f of a divided by b minus a. Or we can say that f of b minus f of a, it should be equal to f prime of c, or derivative of f of c into b minus a. So the mean value theorem can be used to establish, we can say that if our derivative of f of x is equal to 0 for all x in the interval a b, then f is actually, our function is constant on a b. In the interval a b, our function is constant, right? Okay, now we have a very different kind of theorem in this whole chapter actually, and this is really helpful because this really helps us to move or to change the value, actually change the value of a function, and then we can replace value, and after replacing the value we can deal with this particular function, right? And this is known as the L'Hopital or L'Hospitals, you can say L'Hospital's or L'Hopital rule. Both are fine, right? So indeterminate forms of L'Hopital's rule, right? So particularly, it is really handy in order to deal with indeterminate form of type, like 0 by 0 or infinity by infinity. When we have this kind of functions, right, this L'Hopital rule is really helpful in order to the evaluate the limit, right? So basically it says if you take the limit, right, f of x is equal to 0, and where x approaches to 0, sorry, fx approaches to a, and limit g of x is equal to 0 where x approaches to a, then we can say our limit. All right, so if we have these kind of situations over here, suppose that we have these situations and our f of x is equal to 0, g of x is equal to 0, right, and we have this expression in this form where limit f of x divided by g of x. So it clearly means that 0 by 0 or infinity by infinity, right, which is indeterminate, and we cannot determine the values because in order to determine the values we have to have the real numbers, and those real numbers should be able to be solved, right? So in this case we will be ending up with this indeterminate form, right? In other words, we cannot just use a substitution to evaluate the limit. Obviously, when we use the substitution to evaluate the limit, we are hoping for a real number as an answer, right? So if we're not finding this real number as an answer, it's pretty useless, right? So that's the place where L'Hopital rule comes in, and it lets you sidestep the whole substitution process, and the process we have been doing for our limit, for finding the limit, right? We just sidestep that, and then we bring this L'Hopital rule, and in this L'Hopital rule, actually, what do? We find the derivatives of our f of x and our g of x, right? So we find the derivatives of our original values, original numerator and denominator. And really cool thing about this L'Hopital rule is we prepare original functions with, we just prepare the original functions with the derivatives, and still if we are not finding, or if we are finding this indeterminate form, like if we find our derivatives of f of x, right, suppose we find this derivative f of x, f prime of x, or derivative of f of x divided by derivative of g of x, right, and it is still equal to 0 by 0 or infinity by infinity, then we can take the second derivative as well in order to solve it. And we can take, if still it's the same thing, we can take the third derivative, we can take the fourth derivative, and we will be taking the derivative until we just reach that particular point where we can satisfy our answer and we find our relative answer in the real number, right? So that is the concept of actually indeterminate form or L'Hopital rule. You can see over here 0 by 0, it is the indeterminate form, infinity by infinity, right? Or we can say minus infinity, or 0 power 0, 1 power infinity, or infinity power 0. So all these forms are actually the indeterminate forms. So how we can use the L'Hopital rule? So now you can see the example over here. In this particular example, this function is actually in form of f of x by g of x, right? This is f of x, and then we can say this is our g of x, and then we take the derivative of both, and the derivative of x is 1, derivative of tan 2x is 2 secant square into 2x, right? And then we simplify them further, it will be 1 by 2. So it means that we have replaced them with our derivatives of f of x by g of x derivative of f of x by derivative of g of x, and then we were able to be solve these particular indeterminate form expressions, right? We first of all we replace them from indeterminate form to determinate form, and then we solved them, right? Similarly, we have this thing over here, and you can see by just putting in our by taking the derivatives, after taking derivatives we have made them able to be solved in determinate form, and the answer for that was again 1 by 2. All right, so that was actually all about our indeterminate form and the law. So increasing and decreasing test, actually increasing and decreasing tests are whenever our derivative of f of x is greater than 0, it means that the given interval, the function is increasing, right? When our derivative of f of x is less than 0, it means that our function is decreasing on that particular interval, right? Now we can see that when we see from here a to b, it is increasing, right? Because you can see it's greater than 0, right? Increasing. Then here we have this is falling down and it is decreasing over here. Then again from c to d, it is increasing, right? So that is the concept of increasing and decreasing test, actually. Okay, now concave upward and concave downward. So whenever we have our double derivative of x greater than 0 for all x in our interval, then the graph of f is concave upward on interval, right? And if our derivative of x is less than 0 for all the x values in the interval, then the graph of our function is concave downward. So that's very simple thing about the concavity test. Then we have this definition about the inflection point. So guys, inflection point is actually that point on a curve where y is equal to f of x, right? So we can say that this, if our function is continuous there and the curve changes from concave upward to concave downward, or from concave downward to concave upward at point, that is our inflection point, actually, because that is the point from where we just, our concave points are being changed, right? The direction of the graph or the shape of graph is being changed. That is our inflection point. All right, so the next one is actually about the guidelines of sketching a curve. Sketching a curve. So first one is a domain, and we know very well what is domain. It's a complete set of possible values of the independent variable, and actually f of x is defined for the values of x given in the domain, right? So whenever we talk about the domain, we have to know that it would be independent, right? And it would be on x-axis. Our domain would be lying on the x-axis. Then it is intercept, and intercept is actually the y-intercept, which is telling us the curve where the curve intersects the y-axis. The point on the y-axis where a particular curve intersects is known as y-intercept. To find the x-intercepts, we set y is equal to 0 and solve for x. So that's how we just find our x-intercepts as well, right? Next is symmetry. So if our f of minus x is equal to f of x, right, for all x in our domain, for all the x values in our domain, that is the equation of curve is and it's unchanged when x is replaced by minus x. So it means that they both have the same shape, right? They both are in the same form. And if f is an even function, the curve is symmetric about the y-axis. And if f is an odd function, the curve is symmetric about the origin. Now we have to see that if the function is even, right, the curve is actually symmetric about y-axis, and if our function is odd, the curve is symmetric about the origin. And if it's periodic function, we can use a translation of sketch an entire graph. So that is the actually story of symmetry. Now we have asymptotes. So asymptotes are like different kind of asymptotes, but first of all we will know what is asymptote. So asymptote of a curve is actually a line such that distance between the curve and the line approaches zero, right? So whenever it is approaching to zero, this distance is actually being reduced as it approaches towards infinity, right? Distance is being zero or being reduced as the line approaches towards infinity. So basically this line never touches the y or x axis, right? It does not intersect, but still it goes along with y axis or x axis. So when it goes along with the y x axis, it is called horizontal asymptotes. When it goes with the y axis, it is called vertical asymptotes. And when it is in a slant position, right, when it is in diagonal position, you can say of diagonal to the graph of 2D how to say 2D plane, xy plane, or 2D xy plane, and it is diagonal to that, then we can say a slant asymptotes. Right, guys, then we have these local maximum and minimum values over here. These are actually for the test, the first derivative test and the second derivative test over here. So we can just see this in the second derivative test, actually, whenever we have, or suppose we have this double derivative of f, a function, as it is continuous near our point C, right? And if our f prime of c is equal to 0 and f double prime of c is greater than 0, then function has a local minimum at point C. And if our derivative of f of c is equal to 0 and double derivative of f of c is less than 0, then function has a local maximum at point C, right? So that is actually for how to say, to test these are the kind of our derivative tests, right, in order to sketch the curve, right? Then it comes concavity and points of inflection, and then sketch the curve, right? So these were the actually things that are involved in, or these were the guidelines for sketching the curve, right? So that was all about this particular part, like we have studied in our first semester and these topics. Now guys, we have these examples, and you have to go through these examples and you have to solve these examples with your own knowledge, with your available knowledge, right? Do not try to use internet, but your own knowledge which is in your mind. Okay, so in this first example, it says how many real roots does the equation x power 5 minus 7x plus 3 is equal to 0 have in the interval -1 to 1. So you have to choose one answer, but you have to prove that answer as well, right? Then there's another example. In this example, it says find the limit, and this is actually for the L'Hopital's rule. So you have to find the limit for this, and then you have to prove that limit as well, right? Again, evaluate this limit. You have to choose the best suitable answer or the correct answer, and I have shown it myself. Great, I'm so sorry for that. Okay, then we have this example number 4, which is evaluate the limit. So you have to evaluate the limit and you have to tell what's the correct answer, and you have to show the steps of your solution as well, right? Again, you have to find the critical numbers of the function and then find the critical numbers of the function again. So that's all about this particular exercise part. All right, so you have to solve these questions on your own. You can solve on your notebook, and then later you can just take the screenshot and exchange with me. Understand? So guys, that was all, and if you have any kind of problem with them, then we will be discussing it in our question and answer session. So till then, have a good time. Bye bye.